lecture, I will cover the basic probability concepts. These concepts are needed to understand the topics covered in this course. I will start with probability space. You know that to describe probability mathematically, we need a sample space S. This is the set of all the possible outcomes of a random experiment. For example, if I toss a coin, that is the random experiment, because the outcomes cannot be determined beforehand. The possible outcomes are head and tail, and the sample space will comprise of the members head and tail. To define probability meaningfully, we need a class of sets known as the sigma field. The sigma field F, which is a collection of subsets of S, where the probability P is defined. The members of F are called events. We will elaborate these points. Therefore, to define probability, first of all we will have the sample space, then we will have the sigma field F, and probability will be defined on the members of this sigma field. The triplet SFP is called the probability space. I will give an outline of the concept of sigma field. First, I will introduce a field. A field F is a collection of subsets of S with the following properties. Number 1, the sample space S belongs to F. Number 2, if A belongs to F, then A complement belongs to F. Number 3, if AB belongs to F, then A union B belongs to F. So, therefore, the sample space is a member of F, and if A is a member of F, then its complement must be a member of F. Thus, F is closed under complementation. Similarly, F is also closed under union operation. Now, these three properties can be used to derive other properties. For example, the field F is closed under intersection operation. How we can show this? We can show that A intersection B is equal to complement, whole complement of A complement union B complement, that is the De Morgan's law. So, A intersection B is equal to complement of A complement union B complement. Now, A complement belongs to F, their B complement belongs to F, therefore, their union belongs to F, and their complement, that is A intersection B, belongs to F. So, and that way, in this way we can derive the other properties, set theoretic properties, usual set theoretic operations like intersection, set difference, etc. Can be thus the field F is closed under complementation and union operation, and it is closed under other set theoretic operations like set difference, etc. Also, an event is a member of the field. Any member of the field is called an event. The field concept is sufficient to define probability in a finite sample space. But when we have an infinite sample space like the real line itself, then we have to introduce the concept of sigma field or sigma algebra. Field is sometimes called algebra. Similarly, sigma field is sometimes called sigma algebra. Now, first two properties of field and sigma field is common, only third property is different. It says that if n belongs to F for n 1 to infinity, then union of an from n 1 to infinity also belongs to F. So, that means F is closed under the sigma field, F is closed under countable union operation. So, F is closed under countable union. So, sigma field is closed under complementation. The entire sample space is a member of the sigma field and it is closed under countable union. So, we can similarly using the De Morgan's law, we can show that the sigma field is closed under countable intersection also. F is closed under countable intersections. This sigma field is necessary when we define probability on an infinite sample space. I will start with an example considering the random experiment of throwing a die. The associated, it is a finite sample space, the associated finite sample space is S is equal to, it contains 1, 2, 3, 4, 5, 6 corresponding to 6 faces of a die. Now, the power set, which is the collection of all subsets, can be enumerated. For example, S will be a member of this power set, phi is a member. Similarly, I can consider elements singleton set like 1, 2, 3 etc. and doubleton set like that. So, in that way how many elements will be there in PS? 2 to the power 6, that is 2 to the power 6 is equal to 64 elements. It is easy to verify that PS is a field, because if you consider any two member, their union will be a member of PS. Similarly, if we take the complement, for example, if I consider 3, its complement will be the set consisting of 1, 2, 4, 5 and 6, and it will be a member of PS. We also note that the smallest field, what is the smallest field of the subsets of S? If we consider the class like this, S and phi, clearly S union phi will be S, phi union S will be S. So, it is closed under union operation, complement of S is phi, complement of phi is S, therefore, it is closed under complementation, and S is a member of this collection, therefore, this is a sigma field or a field, because it is a finite sample space, we can call it a field, and this is the smallest possible field. Now, what is the largest field? Because PS contains all the subsets, therefore, PS is the largest field. Number 3, smallest field containing a set, set is given by single element only, that is a set consisting of element 5. Now, we can enumerate the sigma field or the field containing this set. First of all, S is a member of this collection, phi is a member of this collection, 5 is a member of this collection, and its complement, that is the set consisting of 1, 2, 3, 4 and 6, that is also member of this collection. Now, this, if I consider this collection of subsets, it satisfies all the properties of the field, therefore, this is the smallest field containing the particular set consisting of element 5. We will consider another example. This time we will consider example for infinite sample space. Example 2, consider the class C of all open intervals of the form AB. This is the open interval on the real line. So, we have considered the open interval like this. This is A, B greater than A, and this interval excluding the endpoints A and B. These are the this is an open interval. Similar open intervals we are considering to find the minimum sigma field F containing C. So, we are considering C is a collection of all open intervals. To be a sigma algebra, what are the other sets that we have to include in this collection? Here S is R and C is defined by this set, and that is the open interval A B, where A belongs to R, B belongs to R. Now, whether closed interval A B belongs to F, we can see that closed interval A B can be expressed as the complement of that is union of the open intervals minus infinity to A, B to infinity, and then if we take the complementation, these are all sigma algebra operation. Therefore, the result, that is the closed interval A B, that is a member of F. Similarly, minus infinity B, this is a semi-infinite, semi-open interval, and this we can write as the union, countable union n is equal to 1 to infinity of the sets, that is we can consider the closed sets minus n B. Now, if I consider the union, countable union of all the sets of this form, then we will get this semi-infinite, semi-closed interval minus infinity to B. Therefore, this also belongs to F. Similarly, we can show that this B is a singleton point, single point set. So, singleton set. So, whether this point sets are a member of this collection. This we can consider as, suppose if I consider B minus 1 by n and B, this closed interval if we consider, and then you do the intersection, countable intersection from n is equal to 1 to infinity, then we will get only one element, that is B. Therefore, this B also belongs to the sigma field F. Similarly, we can consider, we can show that other interval like B to infinity, this will be a member of the field F. So, in this way we can generate a minimum sigma field which starting with the all open intervals, and this sigma field will be called the Borel field, Borel sigma field. So, what is a Borel field and Borel sets? The minimum sigma field containing class C of all open intervals of the form A B is called the Borel field, and it is denoted by letter B. So, we showed in the earlier example how to generate this sigma field, and this sigma field is known as the Borel sigma fields, and all the members are called Borel sets. The same Borel field is obtained if C is considered as the class of all closed intervals. Instead of open interval A B, we can consider closed interval A B of the form A B, that is a closed interval, or the semi open interval of the form one side closed, other side open, or this left side closed, right side open, etc. So, that way we can define the Borel field, and this Borel field is needed to define probability on the real line, and this can be easily extended to higher dimension. Now, we will formally define probability. Probability is defined axiomatically only. So, for a sample space S with an associated sigma field F, the probability P satisfied the following probability P satisfies the following axioms. Number 1, probability is a function on set. So, therefore, this P of A, that is the probability of event A, it is always greater than equal to 0 for all A belonging to F. Probability is a non-negative function. Then probability of S is equal to 1. So, for the entire sample space, probability must be equal to 1. Now, third axiom that is important, if A1, A2 etc. are pairwise disjoint events, that is for I not equal to j, A I intersection A j equal to phi, then the probability of the countable union of disjoint events, this is the probability of the countable union of disjoint events AIs. So, this probability is equal to the summation of the individual probability. So, if we have a collection of disjoint events, their union probability is equal to the sum of the individual probability. This is known as the sigma additivity property. So, with these three axioms, now we can derive all other properties of probability, and any other definition of probability also must satisfy these three axioms. Now, for a finite sample space, the axioms, particularly the third axiom, can be simplified. So, first two axioms are same. So, if S is finite, suppose S is finite, in that case axioms are, what are the axioms? Number 1, probability of A is always greater than equal to 0 for all A belonging to F, that is number 1. It is same as the earlier axiom we have considered. Similarly, number 2, probability of S is equal to 1. Then third axiom can be simplified, and that is if A and B are disjoint events in F, then probability of A union B is equal to PA plus PB. So, this is the axiomatic definition of probability defined on a finite sample space S. Now, other properties of probabilities can be derived using these axioms. For example, probability of S is equal to 1. Therefore, we know that S is equal to S union phi. Therefore, probability of S is equal to probability of S plus probability of phi. So, from which we will show that probability of phi is equal to 0. Similarly, probability of A complement is equal to 1 minus PA. If A and B belongs to F, but then need not be disjoint, then probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Similarly, if three events are there, A, B, C belong to F, then the probability of union will be, now all individual probabilities will be added, then joint probability will be subtracted, and that probability of joint probability of A, B, C will be added. This principle can be extended to consider the probability of union of any number of events. So, that way we define probability using the three axioms, and then also we showed that the probabilities, we defined probabilities using three axioms, and we showed that the other properties of probabilities can be derived using these three axioms. Next, we will consider the conditional probability. Conditional probability, first we have to define, and this definition should be in consistence with the axiomatic definition of probability. Consider a probability space S F P, this triplet sample space S, sigma field F, and the probability P, and two events A and B in F such that P A is not equal to 0. Then the probability of B under the condition that A has occurred. Given that A has occurred, what is the probability of B? So, this we write as probability of B given A. So, by definition this will be probability of A intersection B divided by probability of A. So, this is the definition, probability of A not equal to 0. So, we have to find out the joint probability of A intersection B divided by probability of A, that is the conditional probability. Now, given the conditional probability, we can find out the joint probability. For example, we can write probability of A1 intersection A2, that is equal to probability of A1 into probability of A2 given A1. This can be obtained from the definition of conditional probability itself. So, using this definition, we can find out the joint probability of n events A1, A2 up to An. The joint probability we can find out. What is this? That is probability of A1 into probability of A2 given A1 into probability of A3, the third event we will consider given A1 intersection A2. Similarly, when we consider the last event An, we have to consider all other events A1, A2 up to An minus 1. So, this rule is known as the chain rule of probability. Using this probability, using this chain rule, we can find out the probability of the intersection of events. For example, probability of A1 intersection A2 intersection A3. These three events, their intersection probability will be given by probability of A1, this is first event, into probability of second event given A1, given the first event, into probability of the third event A3 given A1 intersection A2. So, that way we can define, we can find out the joint probability of 3 events, 4 events, etc., using this chain rule of probability. So, we have defined the conditional probability, and from using the conditional probability we showed how we can find out the joint probabilities. Next, we shall consider independent events. So, two events A and B are called independent or statistically independent, sometimes it is called so. If P of A intersection B, this is the joint probability, is equal to probability of A to probability of B. If this relationship is not true, then we call that events A and B are statistically dependent. That way we define the independence of two events. How do I define independence of multiple events? The events, suppose there are n events, they are independent if we consider any sub collection of these events. Suppose AI1, AI2 up to AIM we are considering, and this is a subset of the entire collection. If the joint probability of this intersection of these subsets is same as the product of the individual probabilities, then we say that this event and events are independent. So, we are considering for any subclass, if the joint probability is product of the individual probabilities, then these events A1, A2 up to An events are independent. We can consider an example. We did 3 events A1, A2 and A3. So, when are they independent? So, they are independent if probability of, first we have to consider A1 intersection A2 is equal to probability of A1 into probability of A2, probability of A1 intersection A3, that is equal to probability of A1 into probability of A3, probability of A2 intersection A3 is equal to probability of A2 into probability of A3, and finally probability of A1 intersection A2 intersection A3 is equal to probability of A1 into probability of A2 into probability of A3. So, if all these four conditions are satisfied, then we say that three events A and B are independent. If this condition is, these four conditions are satisfied. Sometimes these three conditions are called pairwise independence, and this condition is condition. So, for three events A1, A2 and A3 to be independent, all these four conditions are to be satisfied. If only first three conditions are satisfied, then the events A1, A2 and A3 will be called pairwise independent. This will give pairwise independence. So, we have introduced the concept of independence. Next, we will go to one important concept, and that is total probability theorem. So, this theorem says that if events A1, A2 up to An, if they form a partition in S, what does it mean? That S is the union of these events and all these events are mutually disjoint. Then probability of B is equal to, this will be the summation I is equal to 1 to n of probability of AI into probability of B given AI. So, if we consider the product of P of AI into probability of B given AI and sum up for I is equal to 1 to n, then we will get the probability of B. This is known as the total probability theorem. We can illustrate this with the help of a simple case. Suppose we have, this is my S and we are considering a partition A1, A2 and A3, and B is an event like this. This is my B. So, what I see that B is the union of this part and this part. Therefore, probability of B will be equal to probability of A1 intersection B union A2 intersection B union A3 intersection B. Now, all these intersections A1 intersection B, A2 intersection B, this is A1 intersection B, this is A2 intersection B, this is A3 intersection B. They are disjoint, therefore, the probability of the union will be equal to the sum of the probability, that is equal to probability of A1 intersection B plus probability of A2 intersection B plus probability of A3 intersection B. So, this now we can apply the joint probability as the product of individual probability and the conditional probability. Therefore, this will be probability of A1 into probability of B given A1 plus probability of A2 into probability of B given A2 plus probability of A3 into probability of B given A3. So, this is the total probability theorem in the case of a partition of 3 events A1, A2, A3, etc. This can be generalized for the any number of events. Now, using the total probability theorem and the definition of conditional probability, we can derive the Bayes rule. Suppose event B is dependent on n mutually disjoint events A1, A2, An. Given that B has occurred, what is the probability of each Ai? So, suppose B has occurred, we are interested to find out probability of any AK you consider given B. So, how we can find out? Now, probability of AK given B. So, this is equal to probability of AK intersection B divided by probability of B. This is by definition of conditional probability. Now, if we write this as probability of AK into probability of B given AK divided by probability of B. Now, we have to find out what is the probability of B, that we can find out using the total probability theorem. So, this will be given by a summation that I will show you. So, what is probability of B? Probability of B is nothing but summation I is equal to 1 to n probability of Ai into probability of B given Ai. So, that way we can find out, suppose the event B has occurred, what is the probability of a particular AK. So, that we can find out using this result, what is known as the Bayes rule. This is due to a famous mathematician named Thomas Bay. So, we can formally state that, let us see. So, this is the Bayes rule. Now, formally we will state this. Suppose A1, A2, An be disjoint events that form a partition, this is a partition on S, and probability of Ai are not equal to 0 for I is equal to 1 to n. So, all these probabilities are known. Suppose probability of Ai's, each event Ai's, that is they are known and none of them is equal to 0. Then for any event B with probability PB greater than 0, now what we will get? Probability of AK given B is given by this Bayes formula. This is the Bayes rule, and now using this Bayes rule we can find out, suppose given some evidence, what is the probability of a particular cause. So, this is very important when we apply probabilistic decision. Let us summarize the lecture. We talked about the probability space SFP that includes the sample space S, the sigma field F. Now, F is a collection of subsets of S satisfying 3 properties. The 3 properties were that S is a member of F, F is closed under complementation, and F is closed under countable union. And probability P is defined using 3 axioms. These 3 axioms are: probability of A is greater than or equal to 0 for all A belonging to F, that is, for all events in F, probability of A must be greater than or equal to 0. Probability of the sample space is equal to 1. Then third axiom was, if Ai intersection Aj equal to phi, that means the events are disjoint, then probability of the countable union of Ai is equal to sum of the corresponding probabilities. So, these 3 axioms were used to derive other properties of probability. So, these axioms were used to derive other properties of probability. We also define the conditional probability P of B given A. This is defined by this relationship. Probability of B given A is equal to probability of A intersection B divided by probability of A. Of course, P of A not equal to 0. Similarly, we could define probability of A given B. Then events A and B are independent if probability of A intersection B is equal to P A into P B. To find the joint probability of any number of events, we use this chain rule. So, according to chain rule, probability of A1 intersection A2 up to intersection of AN, that is given by probability of A1, probability of A2 given A1, probability of A3 given A1 intersection A2, like that up to probability of AN given A1 intersection A2 up to AN minus 1. So, this is the chain rule of probability. Then we derive the Bayes rule using the total probability theorem. So, it finds the a posteriori probability of A k given B, that is given by probability of A k into probability of B given A k divided by probability of B. Actually, if I apply the definition of conditional probability, then this denominator should be probability of B, and this probability of B according to a total probability theorem is given by this summation. Now, here probability of A k, these are the a priori probability, and what we are determining, that probability of A k given B, that is the a posteriori probability. Thank you.